So, we will continue our discussion on Compton scattering. The differential scattering cross section d sigma is given by 2 pi to the power 4 delta p prime plus k prime minus p minus k mod m square, then m divided by 2 p dot k dq k prime divided by 2 pi q 2 k 0 prime and m dq p prime divided by p 0 prime 2 pi q. Now, what we want to consider is, we want to consider the initial electron to be unpolarized, and also we do not want to detect the polarization of the outgoing electron. Therefore, we need to sum average over the spin of the initial electron and sum over all possible values for the spin of the outgoing electron. When we do that, what we need to do is, we need to consider half of the sum over r and s, where s is the spin of the initial electron and r is the spin of the final electron. What we will do is that we will further integrate over the integrate over p prime. Remember, you have this 4-dimensional delta p prime plus k prime minus p minus k, which is nothing but the 3-dimensional Dirac delta p prime plus k prime minus p minus k, and then delta p 0 prime plus k 0 prime minus p 0 minus k 0. When we will carry out the p prime integration, what will happen is, everything will be as it is, except that p prime is evaluated at this value minus of k prime minus p minus k. Okay. So, after performing the dq p prime integration, what we will get is d sigma will be equal to half sum over r is 2 pi to the power 4th delta p 0 prime plus k 0 prime minus p 0 minus k 0 and mod m square m divided by p 0 prime 2 pi q dq k prime divided by 2 pi q 2 k 0 prime, where p prime is equal to p plus k minus k prime. So, you need to replace it everywhere. Wherever you get p prime, you need to replace this. For example, in place of p 0 prime, which is nothing but square root of p prime square plus m square, you need to write square root of p plus k minus k prime square plus m square. Similarly, wherever you have p0 prime, you need to write this, and in the expression for m also, whenever you come across with either p prime or p0 prime, you need to put this appropriately, this or this respectively. Here I would like to introduce something which are known as the Mandelstam variables in processes where two particles come and then interact and then go. So, for example, you have a particle with momentum p and a particle with momentum k going to p prime plus k prime. You can introduce the variables s, t and u such that s is equal to p plus k, t is equal to p minus p prime and u is equal to p minus k prime. These are known as the Mandelstam variables, and it is quite convenient to express the cross section in terms of these variables and to do the calculations using these variables. So you need to keep in mind that the value of p prime is no longer an independent variable, it is this value. Now, what we will do is that we will work in spherical polar coordinate in the momentum space of the outgoing photon. So, the dq k prime we will write it in spherical polar coordinate. What we will get is dq k prime is k prime square d mod k prime d omega. I will call the solid angle to be solid angle in the momentum space for the outgoing photon to be d omega. We will further integrate over this k prime variable and then we will see what we get. Okay. So you can substitute for k prime is same as k0 prime. So, this is k0 prime square d k0 prime, or maybe we will leave it as it is, and then we will keep in mind that since photon is a massless particle, therefore, k square which is k mu equal to 0 and so is k prime square. Therefore, k0 square for k0 prime square for photon is equal to mod k prime square. Okay. This we need to keep in mind. So, whenever you have k0 prime, you need to replace it by modulus of k prime. Then you also have to keep in mind that this p0 prime is, I mean in the delta function, this delta function delta k0 prime plus p0 prime minus k0 minus p0 is not of this form delta of mod k prime minus some a. This is not of this form because of the k prime dependence in p0 prime. So, this is of this form delta of some function of, I will call it as g of mod k prime. So, when you have such dependence, what do you do? For example, if you have an integration over f of x delta g of x dx, then this is same as f of 0 divided by modulus of del z over del x evaluated at x equal to 0. So we need to use this formula in order to carry out the k prime integration. Okay. So what we did is we considered the differential scattering cross section. We have assumed that the initial electron is unpolarized, so we averaged over the initial electron, and also we said that we do not care about the spin of the outgoing electron. Therefore, we sum over all the spin values for the outgoing electron. Then we carried out the integration over the momentum of outgoing electron, and as well as we want to carry out the integration over modulus of k prime. So therefore, what we need is so what we will get at the end of the day is it is just an integration over modulus of k prime, but because of the presence of this delta function, we need to be a little bit careful. Huh? Yeah, sum over zeros of g of x. Yeah.
Not x equal to 0.
Yeah, absolutely. So this is actually integration f of x 1 over del z over del x dg, right? So you are right. So therefore, finally it is evaluated at f of x over del z over del x g equal to 0, not x equal to 0. Eh? What?
M by 2 p dot
Here?
down.
What is missing? Here to here. This is there. Ah, thank you. Okay. This is missing. Okay, good. So m divided by 2 p dot k is already there. So therefore let's carry out this k prime integration. So you have a whole bunch of things, and then you have delta of p0 prime plus k0 prime minus p0 minus k0, and then mod k0 mod k prime square d mod k prime d omega. This is there. So as we have seen, this is just same as the whole lot of things times 1 over del mod k prime of this quantity p0 prime plus k0 prime minus p0 minus k0 d omega, which is evaluated at p0 prime plus k0 prime minus p0 minus k0 equal to 0, right? So what is this quantity here? We have already seen earlier that this k0 is modulus of k prime, and there is a k0 dependence in p0 prime. So therefore this quantity in the denominator is nothing but del over del mod k prime is equal to acting on p0 prime plus k0 prime minus p0 minus k0 is equal to del over del mod k prime. K0 prime I will write as mod k prime, and p0 prime has k0 dependence, which I will keep writing it as P0 prime. Okay. So, this is 1 plus del P0 prime over del K0 prime, right. So, this is what I need to evaluate. So, let's work out dP0 prime over dK0 prime versus d over d which is 1 over 2 P0 prime d over d K0 prime of P0 prime square. Now, it is easy. This is 1 over 2 P0 prime d over d K0 prime of P0 prime square is P prime square, which is P plus K minus K prime square plus M square, right. All right. So, what we will now do is we will work in the laboratory frame where the incoming electron is at rest. So, we will choose P equal to 0, which amounts to saying that P mu is along the time direction, or you choose the time direction to be along P mu. We will use this result later also. So, in the lab frame, this quantity is 1 over 2 P0 prime d over d K0 prime K minus K prime square plus M square. M square dependence will anyway go away because we are differentiating with respect to K0 prime. So, one over 2 K0 prime, let us write it as K prime minus K whole square. So, K prime minus K dot dk prime over dk0 prime, right. K prime is nothing but mod k0 times a unit vector along this direction. Therefore, dk prime over dk0 will be simply equal to k prime over k0. So, this quantity is 1 over 2 k0 prime k prime minus k dot k prime over k0 prime. That is all we got for d p0 prime over dk0. So, I will substitute that here. So, this is 1 plus 1 over 2 p0 prime, then k prime minus k dot k prime over k0 prime. Okay. We can further simplify this result here. So, let us do it again by erasing this part. Somewhere I missed a factor of 2. When there is a square, when I consider del over del k0 prime of k prime minus k square, there is a factor of 2. This is twice k prime minus k dot del k prime over del k0 prime. So that 2 factor will cancel this 2 here, therefore, I will be left with this. Alright, so this quantity now is equal to del over del k prime of p0 prime plus k0 prime minus p0 minus k0 is equal to 1 over p0 prime k0 prime times p0 prime k0 prime plus k prime minus k dot k prime. What is k prime minus k? You remember p prime, 3 vector p prime is equal to p plus k minus k prime, but we are working in the lab frame where p is 0, therefore p prime is k minus k prime. So, I can write k prime minus k is minus p prime. So, this is 1 over p0 prime k0 prime p0 prime k0 prime minus p prime dot k prime. Therefore, this is equal to p prime dot k prime over p0 prime k0 prime. So, what we did is we evaluated this vector and then we found this to be p prime dot k prime over p0 prime k0 prime. We will substitute it here. So, this comes in the denominator. Therefore, when we carry out the integration over k prime, what we will get as a result is this whole thing p0 prime k0 prime over p prime dot k prime d omega. We have to remember that p0 prime plus k0 prime minus p0 minus k0 equal to 0. We have to also remember that we have integrated out over p prime, therefore, p prime is equal to p plus k minus k prime, or in other words we have to remember that we have carried out the integration over the 4 dimensional delta function. So, this provided p prime plus k prime minus p minus k equal to 0. This mu, this 4 vector is 0. Okay. Okay, so now we will come back to this formula here. This integration over this modulus of k prime is carried out already. So, what we are left with is the differential scattering cross section is equal to half sum over r s and then 2 pi to the power 4th, there is no delta, it is mod m square, and then this whole thing will be m square over okay. So, what I will do is that I will cancel this 2 pi to the power 4th with this 2 pi to the power 4th coming from these 2 factors. So, what I will be left is, here there is a 4 pi square and there is a factor of 2 coming from here and a factor of 2 coming from here. So, that will give me 16 pi square, alright. So, no 2 pi to the power 4th mod m square and m square coming from these two factors of m. In the denominator I have 16 pi square, then k0 prime square. Because of this I will get k0 prime square, okay. And then there is a p0 prime k0 prime, and this p0 prime k0 prime in the denominator will cancel this p0 prime k0 prime here. So, what will be left with is, there is a p dot k and there is a p prime dot k prime d omega, okay. Is there anything else left out? So to summarize, what we got after carrying out the integrations is this for the differential scattering cross section, sum over R s mod m square over 16 pi square k0 prime square over p dot k p prime dot k prime d omega, which is evaluated at p prime plus k prime minus p minus k equal to 0, okay. Now, all we need to know is how to evaluate this mod m square, and then we are done. So, let us do that now. So, what is m? M, if you remember from the last lecture, is minus I e square u bar r p prime. I will now put the spin indices because I need to sum over all the spin values, and epsilon slash of k prime 1 over p slash plus k slash minus m, epsilon slash of k plus epsilon slash k 1 over p slash minus k prime slash minus m, epsilon slash of k prime u s p, okay. Now, you remember I need to evaluate modulus of mod m square, okay. In the mod m square, what will appear is, there will be e fourth here, okay. So, I will leave this, I will erase this minus I e square from here, or in other words, what I will evaluate is, I will put a e fourth here, okay, and then I will evaluate mod m divided by minus I e, this mod square. So, minus I e square, I am interested in this quantity, okay. So, therefore, what I will be looking is, instead of writing this factor of I times e every time, I will just concentrate on m divided by minus I e, which I will call as m tilde for simplicity. And so, all I need to do is, I need to evaluate modulus of m tilde square here. Now, in doing this, you can see what you get here. So So, you just combine E square divided by 4 pi you write it as alpha, the fine structure constant. Then what you see is in the formula for the scattering cross section, what you get here is alpha square divided by 2 instead of all these things. You simply get the square of the fine structure constant, and then here you have m square k prime square. Okay, anyway, so that is the reason I want to write it in this way, so that the fine structure constant will appear in the scattering cross section, and also the factor of E will not be there when I evaluate this quantity here. Okay, so now I can simplify these two things by writing this propagator, this Fermion propagator as p slash plus k slash plus m divided by p slash plus k slash square minus m square. Similarly, here in place of this I can write it as p slash minus k prime slash plus m divided by p slash minus k prime slash square minus m square. What is the denominator here in this term? I can simplify that. P slash plus k slash square is nothing but, or let us say this minus m square is equal to minus m square plus gamma mu gamma nu p mu plus k mu p nu plus k nu. Okay. So this quantity again is equal to minus m square plus gamma mu gamma nu times p mu p nu plus k mu k nu plus p mu k nu plus p nu k mu. Okay. What will you get here? Gamma mu gamma nu, this quantity, gamma mu gamma nu p mu p nu is nothing but half. Why is that a half? So this is half gamma mu gamma nu plus gamma nu gamma mu p mu p nu, and this is twice eta mu nu, half times 2 eta mu nu p mu p nu. Therefore, this is simply p square. So this will give me p square, this will give me k square. So this p square is simply m square. So this term will cancel this minus m square. This will give me a 0. So all that I am left with is this. So what is this quantity? This is simply gamma mu gamma nu p mu k nu plus p nu k mu. This is equal to gamma mu gamma nu plus gamma nu gamma mu p mu k nu. So this is twice p dot k. So this denominator here gives me twice p dot k. Here, because of this minus k prime, it will give me minus twice p dot k prime. Okay. So let us write it. So, P slash plus K slash plus M divided by 2 P dot K. Here P slash minus K prime slash plus M divided by minus 2 P dot K prime. This is what I get. I can further simplify these terms. Let's see how. So let's look at this term here. P slash plus K slash plus M epsilon slash of K. I want to bring this epsilon slash to the left. This will simplify this whole term enormously. So let's do that systematically. This is P slash epsilon slash K plus K slash epsilon slash K and M epsilon slash of K. First term is nothing but gamma mu P mu epsilon nu of K. Okay. This gamma nu I can write it as twice eta mu nu minus gamma mu. I will use the anti-commutation relation of gamma mu to write gamma mu to be this. So, this is this times P mu epsilon nu of K. So, as a result what I get here is twice P dot epsilon of K from the first term, and from the second term I will get minus epsilon slash of K P slash. Okay. Similarly, if I evaluate the second term here, I will get twice K dot epsilon of K minus epsilon slash K slash. So let us put these things here together. When I put these things together, what I get is twice P plus K dot epsilon of K from this and this. Then I have minus epsilon slash P slash minus epsilon slash K slash plus M epsilon slash of K. Okay? Yeah, we will use that. We will use that in a moment. So two things we can use. First of all, we know that this US satisfies the Dirac equation, and the second thing is that if this is if epsilon represents the transverse polarization for the incoming photon, then it needs to be orthogonal to K, and also we have chosen the direction of time along P. Therefore, epsilon K will again be orthogonal to P. So, that will simplify enormously, because the Dirac equation tells that there is a P slash minus M here, because I have taken it to the other side. Anyway, let's look at this. So, this term actually it did not simplify, it gave me a complicated expression P slash plus K slash plus m epsilon slash of k is equal to twice p dot p plus k dot epsilon k minus epsilon slash k slash minus epsilon slash p slash plus epsilon slash m. You have to remember that this whole thing actually acts on USP. Okay? So, this acting on USP will give me this whole thing acting on USP, but the last term you can see is nothing but minus epsilon slash k p slash minus m USP, but USP satisfies the Dirac equation p slash minus m USP equal to 0. Therefore, this term is actually 0. So, when it acts on USP, I get this simpler expression twice p plus k dot epsilon of k minus epsilon slash k slash acting on USP. We will further assume that this epsilon k is transverse polarization, therefore, it will be orthogonal to k, and also we will choose, we have already chosen the time direction along p, therefore, p will again be orthogonal to epsilon. So, therefore, p dot epsilon k equal to 0, p dot epsilon k prime equal to 0, because p is along the time direction. On the other hand, since epsilon represents the transverse polarization, it will be orthogonal to the corresponding momentum, 4 momentum of the photon. Therefore, k dot epsilon k equal to 0, whereas k prime dot epsilon k prime equal to 0. Remember, transverse does not mean that k dot epsilon k prime equal to 0, it is not true. Okay, so, do not make a mistake of setting this quantity to be 0, these are the things 0. So, when I set that, this whole thing actually simplifies to minus epsilon slash k slash USP. So, that is what I get from the numerator of this first term. I can similarly simplify the second term. So, let us simply substitute that here. This is u r bar of p prime, then epsilon slash of k, the whole thing here simply became minus epsilon slash k slash divided by 2 p dot k. Here what I claim is, if you do a similar analysis, because of the minus here, it will give me a plus epsilon slash k prime slash. So, this is epsilon slash k, then epsilon slash k prime slash divided by minus twice p dot k prime, this acting on USP. Okay. So, let us rewrite this scattering cross section. D sigma or we are evaluating mod m square m over minus I e. This is the quantity that we are looking at. It's a u r bar p prime, then there is an overall minus sign coming from both the terms, epsilon slash k prime, epsilon slash k slash over twice p dot k. Now epsilon slash k prime slash divided by twice p dot k prime acting on USP. So what we need to do is we need to compute the mod square of this thing. So this is of this form, some u bar r p prime, some operator O USP. So this is of this form. All we need to find is m over minus I mod square. So therefore we need to consider this quantity u r bar p prime USP mod square, where O is the operator, minus epsilon slash k prime epsilon slash k slash divided by twice p dot k plus epsilon slash k prime slash over twice p dot k prime. Okay. So I square. Okay, thank you. Okay. So what we will do is that we will evaluate this, and then we will show that this quantity is actually equal to trace of O p slash plus m over 2m gamma 0 O dagger gamma 0 p prime slash plus m over 2m. This is what we will be showing in the next lecture, and then we will evaluate this trace here. So you can see that something similar should come here, because you already know there is a mod square, and at the end of the day you will get some expressions which involve USP u bar s USP u bar sp sum over s, and we know this quantity is nothing but p slash plus m over 2m. Okay. So we will use similar relation twice, and then we will write the things properly. At the end of the day we will show that this is equal to this. So ultimately what we see is that evaluating mod m square actually turns out to be evaluating the trace of a bunch of gamma matrices. So finally we will evaluate this, and then at the end we will get this whole square, this modulus of this quantity square, to be some function of p and p prime, which we will get a nice expression for p and p prime, which we will plug in the scattering cross section formula, and then we will see what we get. Okay.